Very Ryan. Good, good. Yeah, good. Okay, so today we talk about checking if two trees have the similar leaves. So for example, like this tree, 1, 2, 3, 4, 5, and then this tree, 1, 4, 2, 3, 4. Okay, maybe I will do this. Another one. 7 and
You're doing it from
6,
mirror.
4, 7. Okay, so there's a 4 here. Okay, so these will be, yeah, just get rid of it. Okay, so now look at the leaves. What are the leaves of this binary tree?
1, 2, 3, 4.
Leaves.
3, 4, 7.
3, 4, 7. 3, 4, 7. What are the leaves of this binary
3,
tree?
4, 7.
3, 4, 7. Okay, so we return true if there are leaves in the from left to the right order is 3, 4, 7. Okay? So if I have another one like 8, then this will return false because the 8 is also the leaf. Okay? So these are not equal. So do you understand the problem? Ryan, do you understand the problem? Ryan?
Yeah.
You understand the problem, yeah? So any ideas? Any thoughts?
You just check the leaves.
Yeah, what we're done. We just check the leaves. And how do we check the leaves? How do we first of all, how do we check if the node is a leaf?
It has no children.
We're done. Yes, exactly. It has no children. If a node has no children, it's a leaf. Alright? Yeah? Just remember the tree is upside down in computer, yeah? This is the root. But in the real life, the root is down and the leaves, yeah, growing upwards. But in computers, the tree is growing downwards. Okay? So that's the root. That's the leaves. That's the branch. That's the trunk, yeah? We call it trunk.
Trunk.
Yeah? Trunk.
Like an elephant has.
Yeah, exactly. Okay. So look, you mentioned something very important is how we checking the leaf is that we check if a node has no, does it have any children. If it doesn't have any children, it's a leaf node. But another thing to see here is that we need to record the leaf nodes from the left to right. So do you remember which how are we traveling the trees usually? Which kind of
Breakfast search.
breadth search? Yes, exactly. Breadth search. This is travel from level to level, yeah. And another one compared to where down, yeah, depth first search. So okay. So which one do you think is better suited in this case?
Breakfast search.
Why is that? Yes, you are right. Depth first search. So we go left, yeah,
Yeah.
as deep as we want, and then until we meet the leaf node, then we know we meet the leaf node, right? And then we go back. We find the 4, yeah. Go back, and 7, yeah. This is the travel, yeah. And then this is the sum. So we first of all we need a functions to travel a tree from the root, and then we record the leaves as we do the traveling depth first search, right? And at last, we just need to compare if both depth first search produce the same sequence. Am I right? Yes? Okay, let's write it. We're done. It's the depth first search, okay? So first of all, we need to check, let's say, same leaf, okay? Same leaf. Leaves, plural, yeah? Same leaves. And then, let's do this A and B, yeah? So there are 2 nodes. 2 trees, A and B, okay? 2 root. So we can have another function inside. Okay, look, we call it depth first search. Yeah?
Yeah.
And then let's call it the root. And then, can you tell me what I'm missing?
Column.
How many columns?
1.
How many columns?
1.
So that 2. Okay. So look, if root yeah, you know this before, yeah? It's none. Yeah? Then we should return
3 columns.
return what? We want to return return what? We want to return an empty bracket, which is empty list. I'll tell you why it's empty list, okay? So if it's the root,
Because
it's
it doesn't
none.
have any leaves.
That's right, yes, it doesn't have any leaves, empty. So basically, this function will return a list of leaves in the order, right? And if it's none, it means there's no leaves in the bucket. You can say it's a bucket, yeah? Bucket, you're gonna a list, yeah? Okay? Then, if root dot left is none, and root dot right is none. So what does it mean here? What does this mean? If root dot left, if this root dot left is none and root dot right is none, what does it mean?
The leaves.
It's a leaf, no. Yeah, well done. If it's a leaf, no, then we return what? Yeah, remember, if it's a leaf, no, we need to return a bucket with a leaf, with current leaf. Yeah? Yeah?
Mm-hmm.
So this bracket, but root dot value. Yeah, does it make sense?
Yeah.
Yeah? Yeah?
Yeah.
Okay, then now we recursively, we just need to return depth first search root dot left plus depth first search what? Can you guess? We are returning the left and the right. So what does it?
Root dot right.
Root dot right, yeah. So does it make sense? If it's not a leaf node, if this is not leaf node, yeah. So the final sequence will be the leaf nodes in this bucket, in this tree, plus the leaf node on the right tree. So we put it together. All right? Yeah. Let's go there for search. And here, if we want to compare if two are the same, so return what? Can you guess? We have this function. So therefore search A. What? This is the leaf order of the tree A. We want to compare if it's the same as the depth search of root another tree. So what should I write here?
Something about B?
Yes, something about B. What about B? Depth search B, huh?
Yeah.
And depth search B. So what should I put here?
Equal?
How many equals?
2?
Yes, well done. Wow, be confident. Come on, you're right. Yes, too confident. Does it make sense?
Yeah.
So look, this function we define to return previously we have 1, 3, 4, yeah? Yeah, 1, 3, 4. So 1, maybe 3, maybe here. 3, 4, yeah? Yeah? Yes? So this was return 1, 3, 4, yeah?
Yeah.
And then another tree, different structure, but it also return 1, 3, 4, and we compare if it's the same. So these, look, if a root is long, return an empty bucket with no leaves, yeah? Because if it's nothing, it's air, it's not a leaf. If root dot left is none and root dot right is none, it means that if the current node is the leaf node, then great, we just return a bucket with itself. Otherwise, this is not a leaf node, right? And then we just need to recursively travel the left tree and the right tree. Because the left tree and right tree, we know how to solve it. We already know it. And then after we get the result, we put it together. Yeah, so DFS root dot left is 1, right? Yeah? And then DFS root dot right is 3 and 4. So plus 3 and 4. So this is list, yeah? A bucket with the list 1 plus a bucket with list 3 and 4. What does it equal? A bucket with 1, 3, 4. Yeah? Got it? Yes? Well done. What's the term complexity? Guess. If there are n number of nodes in the root A and m number of nodes in the root B, so what's the term complexity?
N and B. N and M.
Yeah, well done. And what's the space complexity? The same, yeah?
Yeah.
So why is it all n plus n? Because we need to travel all the n nodes in the one tree and the m nodes in another tree. Yes? Yes, okay? Yes, okay. Close your eyes. Close your eyes. I'm gonna erase this. Okay? Right, come on.
Return something.
Yeah, if current node is a leaf node, what will return?
If current.
This is the current node is the leaf node. And then remember, we want to return a bucket with the current node.
What does that mean?
Return, you just write it down, return.
Okay, return first.
Yeah, well done. If the current node is the leaf node, yeah? Yeah, current node is leaf node. Right, are you okay?
And
Bracket.
bracket.
If the current node is the leaf node, like 1.
Yeah.
Yeah, and we want to return the leaf node, which is 1. Yeah. So what do we want to put inside? The value of the node.
Yeah.
So what's it? Root dot value. Yeah.
Yeah.
Yeah, you can do it. Root dot value. And then bracket.
Done.
Well done. Yes, that's what we want. Okay. Any questions?
No.
Okay, so let's say bye bye to people and see you tomorrow.
Bye.
Okay, bye bye. See you tomorrow.
Bye.